Good morning. Our presentation today is on designing magnets. My name is James Hunter.
I'm Kristen Kirchhoff.
I'm Ron Wilson.
I'm Eric Bell.
I'm Ben 10.
And we are this semester's ECE 480 Design Team 6. Today we're going to go over a few types of magnetic materials, ferromagnets, diamagnets, and paramagnets. And specifically we'll go into neodymium magnets, which are what we're using for our project this semester, identify what type of magnet that is and how we're applying it. After that we'll talk about electromagnets, and again more specifically solenoids and how a current through solenoids can generate a magnetic field and how we're using it for our project again. Following that we'll talk about some design considerations that we should take into account when designing a magnet. And then we'll talk about how we're using electromagnets and neodymium magnets together to create a product like we're doing for this semester's project. And then at the end, we'll compare neodymium magnets to other type of naturally occurring magnets and see how they compare and contrast. So there are three basic types of magnetic material: ferromagnets, diamagnets, and paramagnets. You're probably most familiar with ferromagnets because they are the most common and strongest type of magnets. They're essentially the type of magnet that you played with as a kid, where you have two magnets and they attract an object to it, or your refrigerator that you can stick stuff on. Those are ferromagnets because they have their own magnetic field. So how does an object like iron or cobalt create a magnetic field? The atoms have magnetic moments, and they are all aligned in certain magnetic domains. Once the temperature of the type of material drops below a point, that's when they create these domains. And you can see in the picture on the right that the domain, the atoms, the magnetic domain are all aligned in the same direction, although each domain may be in a different direction. After the introduction of a magnetic field, the domains will align, and a permanent magnet will be the result of that. So that's how different types of materials like iron will become their own generating a magnetic field.
Okay, unlike ferromagnetic materials that's really strong, paramagnetic and diamagnetic materials are a little bit weak and really relies on the magnetic field. So like the paramagnetic materials are affected by externally applied magnetic field. So basically without a magnetic field, it won't have magnetization. And also diamagnetic materials are field, so just like paramagnetic materials, you definitely need a magnet field for it to work efficiently. And we're using neodymium, which is a compound element, a chemical element, Ag. As you see in this picture, it's a silver, like soft material, which like tarnish in air. It's actually a rare earth material, which is mainly mined in China. And this common material is like really used in like electrical motors, computers, generators, speakers, things like that. And we're using the neodymium magnet for our project, which is really strong, like we said. The pros and cons to this is that extremely high energy products, so it's like for any smaller compact product, it's definitely good to use for small applications. It doesn't overheat, so it has like temperature stability, and it's also low cost. And the cons of it is that it corrodes pretty easily, but over time, and also lower mechanical strength in Alnico, and we'll talk about that a little bit later.
Okay. I'm going to discuss electromagnets a little bit, and these specifically, we are utilizing electromagnets in conjunction with the neodymium magnets. The reason for that is that the electric field that we can create with the electromagnet will affect the neodymium magnet in the manner that we intended, since it is a paramagnet, as Laurent explained. Basically, a coil will produce an electric field from the motion of electrical charges. we send a current through the wire. As you can see here, current flows through the wire and a magnetic field is created. Real basic formula for that, the force created equals the magnetic field squared times area over 2. Mu is actually a magnetic constant. Specifically solenoid, and then the magnetic field, B, which would go into the other equation there, is just the number of windings over the length times the current that we'll be sending through it. And this is specifically, that is an equation that we needed to utilize to complete our project. Some examples of functions that magnets can be used for: mechanical to mechanical, as in two magnets clunk them together, things like that. Mechanical to electrical, generators and microphones, things that everybody uses. Electrical to mechanical, motors, loudspeakers. Mechanical to heat, eddy currents, induced currents from magnetic fields. Hysteresis, torque devices, brakes, some types of brakes and things like that. And then special effects that can be seen from magnets, magnetoresistance, different strength resistances created by magnets, Hall effect devices, so induced voltage, and magnetic resonance, which of course is radiation. Those can be used in various types of devices.
So when designing a magnet, it's important to realize that the basic problems revolve around the distribution of magnetic flux. It is also important to understand the properties of the material in order to magnetize it. And the basis of the design is based off the BH curve, where B is magnetic flux, which is a magnetic induction over a certain area, and H is the magnetic field. It's also referred to as a hysteresis loop, and it characterizes each magnetic material. So in the BH curve, for the first quadrant right here, we have saturation, which is where you're increasing the magnetization of it into where you're increasing the magnetic field until you can no longer increase the magnetization of this material. And the B strength right up here starts to level off, and then we move into magnetization in the second quadrant, followed by saturation in the opposite direction and demagnetization from an external field in the fourth quadrant. This is kind of how your hard drive would work when writing material to it.
Okay. When we were thinking of the solution to the Taskmaster's design that had a vibrating pins, one idea was to use the magnets to stabilize the pins. For an previous prototype that we detailed in our previous presentation, we designed a solenoid to create a magnetic field that would attract or repel the neodymium magnet. The picture on the left shows the previous prototype utilized neodymium magnets in the solenoid. By sending the current through the solenoid, a magnetic field will be generated that drives the pins up and down, as indicated in the diagram on the right. This diagram shows the in-depth how the polarity is affected by the solenoid. The polarity changes depending on the direction of the current in the solenoid. By reversing the current in the solenoid, we were able to reverse the polarity. The reversing of the polarity is what caused the pins to move up and down. For our latest prototype, we designed a new circuit that drives the pins horizontally. It works at the previous prototype. We changed our physical design to make the pins more stable by however, we still use the same concepts through utilizing the solenoid and creating the magnetic fields. As you are watching, look for how the current through the solenoid to drive the pins horizontally. This design successfully stabilized the pins. This is our video. So this is our circuit. And this is our prototype. And you can see the solenoid here, and the magnets will like move the pins up and down.
So there are other materials besides neodymium that could be used. We'll go over some comparison with them, pros and cons, and kind of why we chose not to use them then. So the first one is Alnico, then ceramic, and samarium cobalt. So Alnico is an alloy of aluminum, nickel, and cobalt. It has a good temperature stability, which means that it can work in different temperature environments. High corrosion resistance, so we wouldn't have to worry about it corroding if it was in some kind of moisture environment. And then it has a high mechanical strength, so it wouldn't be prone to breaking or being crushed by anything. The only problem is that it is prone to demagnetization, so that wouldn't be very good for our project. In case that did happen, the pins would no longer move up. And it has a low energy product, which has a weaker magnetic strength, essentially, and it is higher in cost. Ceramic is a composite of iron oxide and barium carbonate. It is very commonly available, which makes it lower in cost. And it has a high corrosive force, which means that it has a very strong magnetic strength. It is also resistant to corrosion, which would be good if the environment was in some kind of moisture or anything like that, where we'd be worried about maybe rusting or eventually the magnets corroding. And it also has a high heat tolerance. The only downside to that is that it does have a low mechanical strength. Then for samarium cobalt, that is highly resistant to oxidation. It has a high magnetic strength compared to ceramic and Alnico, and it is better, has a better temperature resistance than neodymium. But the problem with it is it is, has a low mechanical strength. It's brittle, prone to chipping or cracking, and it is expensive.
So today we went over an introduction to different types of magnetic materials. We gave you an overview of ferromagnets, diamagnets, and ferromagnets. We talked about how we're utilizing neodymium magnets and what type of magnet that is and how it's useful for our project this semester. We went over some electromagnetic principles and how we are using solenoids and current driving through solenoids to create magnetic fields and how we're using that for our design. We went over some design considerations, and then we showed you some real-life examples of how we're applying that through our current prototypes and how it's evolved through the process. And then at the end, Kristen talked about the different types of materials as opposed to neodymium. This concludes our presentation. Are there any questions?